we'll have to think about that a little. There'll be some examples today. So the way we represent a vector graphically is with an arrow. The vector has its 2 points and a line segment between them, and we usually draw a little arrowhead on the front. The front we call the head, and the starting point we will call the tail, or the book uses the word tip, which I've never seen before, but I guess that would be one term. So you can think of it also as like a directed line segment. It's a line segment which has 2 points. The line segment has some length or magnitude, and it goes from the tail to the head. We're going to use some notation here. We're going to use, when we give a vector a label, like give a point a label, like A, we'll call vector V, and we'll draw a little arrowhead above it. Not usually this large. If we're describing the vector by 2 points, the tail and the head, let's say those are points A, B, we would write it this way. We would say AB with an arrow over it. And the order is important. A is the tail and B is the head. And we don't ever write it with the arrow going the other way. I guess we could. There's no purpose for that. So this is like a label, or it could be a variable that describes something which is not a number, it's a vector. So it's going to have a direction and a magnitude or size. The magnitude of a vector is always positive. And let's see, what do I want to say here? Okay, so we have a technical name for the magnitude, which is called the norm, N-O-R-M. And there are 2 versions of notation to show this. The book uses the one on the left, but I found in mathematics the one on the right is more common. The one on the left, you could think of it as like the absolute value. It's not really an absolute value, it's a norm. The vector also has a direction which we represent graphically by the direction that an arrow is pointing. So, for example, if I were to draw a vector this way, we would say the direction is 0 degrees or 0 radians. Straight up would be 90 degrees or pi over 2. Okay, I guess I should specify, we're going to talk about 2-dimensional vectors. Vectors can exist in more than 2 dimensions, in which case we would need to be a little more elaborate about specifying the direction. But for right now, we're just going to use the same strategy that we've used all along in finding the direction of or the angle of an angle. I guess that's what I'm thinking of, an angle. Now, having said that, some of the problems we're going to do are going to be from aviation. An airplane going in a certain direction. And for purposes of aviation, there's a different standard, which is pretty obvious. You just have to make sure you know which of these you're using, which is we're using a compass. and in particular north is 0 degrees, south is 180 degrees, east is 90 degrees, and west is 270. And so if you get an aviation problem, this is what you're going to want to do. Also note that that angles increase clockwise. Normally we have them increasing counterclockwise. So just something to keep in mind when we get to problems. Okay. Here's some graphic examples. Here's a vector. Its magnitude is 7 centimeters. Its angle is 45 degrees. Here's a vector 90-degree angle, 5 centimeters. We also can have an obtuse angle, 120 degrees, 2 centimeters, or a vector pointing back the opposite direction is 180 degrees, and all the way around. And just like any other angle, you could have an angle greater than 2 pi or greater than 360, but it's redundant, or it's I guess we did some problems where angles greater than 360 have some meaning, like if something's turning. But in this case, you don't gain anything by having a vector greater than 360 or 2 pi. Okay, now here's kind of the tricky idea here. A vector doesn't have a specific position. In other words, a vector has a magnitude and a direction, but from where, right? Unless we locate it somewhere, it's kind of, you could think of, there's a vector pointing from where I am in the front towards the back, but you could put the arrow anywhere, right? And it just has the meaning of some kind of quantity, like velocity or distance, in that direction. Thus I have this diagram here. It's never kind of worked out quite as well on the overhead. These are all arrows that I've drawn that represent the same vector. They're all in the same direction, they're all the same magnitude. So they're represented by an arrow in a specific position, but I want you to think about this. You can move that position around without changing the vector. So how do you go about doing that? Well, zoom in a little here. If I have a vector from point A, B, and it goes to C, D, call that capital A and capital B, we can move it by adding the same x displacement and or the same y displacement. So you can see here, I've moved in the x direction, a delta x, both the tail and the head's x coordinate, and I've also moved the y coordinate at some value delta y. This does not change the vector. It's the same vector, right? You look at it and say, what direction is it? Well, how would we find out the direction? Well, we find the slope, and then we find the inverse tangent. How would we find the magnitude? We'll get to that. We're Pythagorean theorem. Okay. So, given that you have some vector, there's this nice thing you can always do with it, which is you can move its tail to 0. That's very easy to do. If you have a point, a vector that goes from AB to CD, it's the same vector goes from 0, 0 to C minus A and B minus D. So I'm just subtracting the coordinates, or if you like, you know, you think, here's my axis, and what I'm doing is I'm moving this over A in the x direction, and then I'm moving it down B in the y direction. And this is very important because we have a name for this new type of vector. Oh, here's actually an example with numbers, right? So I have a vector that goes from 2, 4 to 6, 7, and now I've moved it to 0, 0, 4, 3. It's the same vector. We have a name for this. This is called a position vector. I'm going to put it out here. Position vector. Position vector, a vector that starts at the origin. Right? So if I have a vector, a position vector, V, the 0, 0 is redundant, and I will write it this way. I will use angle brackets to represent it. And 5, 7 represents the head, but the tail is implied. The tail is 0, 0. And we call this format in particular, we call this the component form. Component referring to, this is the x component, this is the y component. So that's nice. We can express a vector as just a two-dimensional vector as just two numbers. It's x coordinate and y coordinate of the position vector. If you express, another nice thing is if you express a vector in its component form, it's unique, right? So if I move it around, I might go, is these the same vector? I have to check. But if I put a vector or two vectors into component form and their x and y coordinates are the same, then it's the same vector. That's one way you can check to see if a vector is, two vectors are the same. Okay.
Professor?
Yes.
One quick question, kind of silly, but the
Yes.
brackets that were around the vector component form, is that specific to that form? Like if you need to put it in
You can use brackets for, we use brackets for a lot of things.
No, I'm saying they need to be those specific brackets or parentheses is fine. Just out of curiosity.
Well, I'm using, okay, so here's a thing in mathematics, right? Somebody wants to develop some new form of mathematics. They can make up whatever, what's the word I'm looking for? Notation. They can use whatever notation they want, right? They can say, we're going to use square brackets for this and angle brackets for that. As it turns out, vectors is so common that different books will do different things. I'm following what your book does. It uses these angle brackets for vector component form. You will at times find books that will simply, you'll see, V equals parentheses 5, 7, which can be confused with a point, right? This is an ordered pair, represents a point. It could be an open interval, right? I mean, we reuse the notation, so you have to understand the context. In particular, the book uses this angle bracket for the vector component form. Okay, I mean, good question. I mean, these things can be confusing, especially if you take this and then you go to your physics class, and your physics professor may do it a little differently, right?
Thank you.
Right. Am I going too fast? There's a lot here. There's a lot here. It all ties back to what we've been doing, but okay. The next issue is, given vector component form, how can we find the magnitude and how can we find the direction? And this should be pretty straightforward. You have a a vector, which is A comma B, right? We know that the coordinates A comma B are here. This will be length A, this will be length B, and immediately we can see that the Pythagorean theorem comes in, right? The magnitude or norm of the vector is just the square root of the sum of the squares of the components. This isn't part of today's lesson, but if we were using a vector in 3 dimensions, you know, A, B, and C, we would just extend this, we would just extend this to the square root of A squared plus B squared plus C squared, which is just the Pythagorean theorem, 3 dimensions. The direction, we can find the direction sort of using the arctan function. We know I guess you can think of this A over B, but y over x, the slope, right? That's the tangent of the line, of the angle. But again, as we've been doing, you have to be a little careful, right? You have to think, wait a minute, which quadrant am I in? If y over x is positive, that could mean either both x and y are positive, or x and y could be both negative. If x and y are both positive, the arctan is going to give me the right angle in the first quadrant. But if both y and x are negative, it's going to be that vector the vector is going to be in the other direction, and you're going to have to add 180 degrees to the angle. This is just like we've been doing with angles. Okay. All right, that's kind of the basic. Now we're going to start exploring what you can do with vectors algebraically. With numbers, you know, there's a number of things you can do with them. You can add them, subtract them, multiply them, divide them, if one of them isn't 0, right? You can do all sorts of things. With vectors, we have to be a little more careful, but the first thing we're going to look at is adding vectors. You can add any 2 vectors, and you're going to get a new vector, which is going to be called the resultant. Right? That's just terminology that the book is going to use. There are 2 ways we can go about this. The first way that we're going to learn is we can add vectors graphically. Now remember, you can move vectors around. You can move the head and tail around. And if you have 2 vectors, I'm going to use the vector labels u and v a lot. So if you have a vector v and a vector u you want to add, you take the tail of u and put it at v, at the head of v. And now you have the tail of v and the head of u is now the new vector, which is the sum of these 2 vectors. Now, I want you to notice something here immediately, which is if I take v and I put u at the tail of u at the head of v, I get a vector. But if instead I start with u and put the tail of v there, I also get the same vector, right? What I've got formed here is a parallelogram, and in both cases the sum of the 2 vectors, you know, that are the sides of the parallelogram, are this diagonal of the parallelogram. Sometimes you'll hear a reference to the parallelogram rule for adding vectors. So, assuming we have some kind of standard, we say the first vector is first one here and the second one is the second one, you can see we now have this nice property of vector addition, which is that it is commutative. As we go along, I'm going to mention certain properties, and I want you to think about numbers, right? Numbers are also commutative, right? If I add A and B, of course, I can add B plus A and I'll get the same thing. Let me just kind of jump something in here. We're not going to prove this right now, but in fact, if you want to add three vectors, let's say U plus V plus W, right? You have to decide which to add first. So we could add U and V, but we also could add V and W first, and then add U, and we would find that they're the same. Vectors have this other property, which is called the, you know, everyone learned this in high school. This is the associative property, right? Numbers have this property too. All right, that's one way to add vectors. That's kind of the hard way. The easy way is you put your vectors into the component vector form, and you just add the components. And that gets you your new vector, the sum. Let's try and take a look at something that kind of illustrates that. Here I have a vector 1, 2. And I'm going to add to it this vector, which is, it's going from 1, 2 to 4, 2. I'm sorry, this is just the vector 4, 2. I could draw it in here, but it would mess up the diagram. But you can see, this is just the x component of the first vector, and I'm just, say, call it x1, and I'm just adding that to the x component of the second vector. Oh, I'm already getting confused. These are y's. Here's the x, first component of the x vector, the x component of the first vector. There's the x component of the second vector. So you can see, this is really nice. All I have to do to add two vectors is just put them into this component form, and I just add the components. That makes it seem so simple, you wonder why we even make a big deal about it.
I have a question.
Yes?
The last one, the like 4 and 2 and 1 and 2 is like the y coordinate is same, so.
This is 2 and this is 2, right?
You mean?
Right?
So it's
So
supposed
that-
to be like
so
4 and 4, isn't it?
I'm sorry?
It's supposed to be like 4 and 4, no 4 and 2.
Something's 4 and 4? Are you asking if I have 4 and 4?
I don't know, like you added 2, right?
Okay, in the y direction,
Oh, yeah.
the components are 2 and 2, right? So
Yeah.
the resultant, the y component is 4. In the x direction, in this example, the first component is 1 and the second is 4. And
Oh, sorry.
I add those and get 5.
Thank
Okay, just needed to look at it for a minute.
you.
Okay, is that all clear?
Yeah.
Okay. Well, if we can add vectors, what would we like to do? We'd like to subtract them. Did you say subtract them? Did you say subtract them? Yes. We'd like to subtract them. And the way we're going to subtract vectors is kind of the same way we can think of subtracting numbers, which is subtracting a vector is adding its opposite, which I'm writing in by putting a negative sign in front of the vector. Well, that begs the question, what is the opposite of a vector? Right? Well, you have a vector going in one direction, a certain magnitude. The opposite of the vector is a vector going in the exact opposite direction, but the same magnitude. Just as a point of reference, you might want to notice that if I have a vector whose components are a, b, the opposite of that vector just has components that are the negative values. Okay, so let me make up something here. So if I have a vector v, which is what I would call x1, y1, and I have a vector u, which is x2, y2, then vector v minus vector u is just x1 minus x2, y1 minus y2. Pretty much the same, what you'd expect, given what adding is like. However, what does this turn out to be graphically? So this diagram is a little complicated, but let's just take a piece of it at a time. So here I have a vector v, and here I have a vector u, and I want to find out what v minus u is. So I know that I'm going to add to v negative u. Okay, so here's negative u, right, from here to here. So what I want to do is add my vector v to my vector minus u, again using this parallelogram rule, and that's going to be this vector here. Now, what I want you to notice is that when I was adding two vectors, when I was just adding two vectors, the new vector was out here, the diagonal of this parallelogram. But when I subtract them, what I end up with is the other diagonal, the one that would go from head to head. So whereas this would be v plus u, this one is v minus u.
I have a question.
Yes.
If you add v, like the vector v and vector u, what is, like, and then you get another line, what would you call that line? Or would it just be vector v?
If I add vector, like this vector v and this vector u,
Yeah, and then you get a new vector, like what would you,
that's this vector.
yeah, but is there a specific notation, or is it just vector v?
Oh, I mean, let's say I want to give it a name, right? So I'm going to give it a name w. So w vector equals vector v plus vector u. I mean, this notation here is saying the sum of these two vectors. There's no, I guess I've seen somewhere, I don't really like it, but I've seen this. Kind of like that. It's a little confusing. Where did the v and u come from? But that would be acceptable, I guess. I mean, the important thing with notation is that it's clear. If you're confused about the notation, it can get a little dicey. Okay. Okay, I'm gonna do a little summary here, and then we're gonna do some problems. The purpose of this summary here is to compare numbers and vectors. So the first property I want you to recall, I can add any two numbers, and I always get a number. I can add any two vectors, and I always get a vector. And this is that weird property that you probably wonder why they even make a big deal about it at all. It's called closure. Not everything has closure, right? I mean, if you wanted to add two positive numbers, you can always get a positive number. But if you wanted to subtract two positive numbers, you don't have closure because you could get a negative number. Okay, the second property I talked about, numbers have it A plus B plus C is equal to A plus B plus C. Vectors also have this property, it's the associative property. And then we saw that A plus B plus B plus A. Vectors also have this property, B plus U is U plus B, that's the commutative property. Okay, now we're going to add a little information here. There's a number called 0, which I can add to any real number and get that number back. And you might recall that's called the identity property, and 0 is sometimes called the identity or addition. There is a vector like that, right? And I'm going to close in. We draw it this way, a 0 with a little vector sign over it. You want to be careful. The 0 vector is not 0. Right? 0 does not have a direction. 0 vector sort of has a direction. It's actually any direction, which is kind of weird. But it's distinct from 0. But it does have that property that you can add two vectors. When one of them is the 0 vector, you always get your vector back. And so we again have this identity property. And the 0 vector is the identity for vector addition. Finally, very important property of numbers, every number has an inverse. If you have a number A, minus A is the inverse. Inverse is minus 5. What's its inverse? 5. Yeah. Just multiply by minus 1. And inverses have that property. When you add a number to its inverse, you always get the identity. Vectors are exactly the same. You add a vector and its inverse, you get the 0 vector. All right, that's the inverse property. Okay, what I'm going to do now, I'm going to give you guys a few minutes if you want to take a break, but I'm going to pass out a worksheet. It's just going to ask you to do, this is just the first page, there's 4 problems, and it's just going to ask you to do a little work, add some vectors, draw some vectors, get a little practice with this. So you can work on it now, or you can go get something to drink, something to eat. Actually, why don't you come up and get them, since you're on. And if you have, yes, you have exam questions.
Just on both of them, he gave me yours, and he's like, check that, and I'm like,
I have to.
I thought he was joking, and he gave me yours, and I was like, oh no.
How did I do?
I don't know, I had to see the video, I just like, no, I'm not gonna be.
Problem again. So.
Here you go.
That's real basic too. You have one too?
Ya todos los
This is exactly right. This is not exact, precise.
No, the word.
No rounding, no error, right?
But is it test or, because I mean, we dropped
So
the
beat me up. Don't think you
And
can get
then
away
for
with it
midterm?
too often. Okay.
when it comes
Okay, do we have, let's see. Ouch. Ouch. I didn't show you how to do multiplying by vectors yet. Ouch. Nobody said anything. I hope you didn't try number 1. Flow, tension.
Please stop talking.
Yeah, stop playing. I was at 8 o'clock, I was like I've actually been working on this lecture for like 2 weeks. And thought, I'll have some time tomorrow night and I'm gonna coordinate these problems with the lecture. And then something happened at around 7 or 8 last night. And I couldn't really do anything. Anybody understand that?
Yeah.
I gotta stop for just a second. Compose myself. Okay. It's been a rough couple of 24 hours. All right, so I'm sorry. I'm gonna show you how to multiply vectors by constant. But I did show you how to add a vector, and I'm hoping that you say you could have done it this way, right? We are vector 2, 2, and I'm going to have a vector. Try on any piece of paper. I got paper. I'll just grab one of these. All right, so I've got these 2 vectors. 2, 2, and minus 2, 1, 2, 3. 1, 2, 3. Okay? So I want to add these 2 vectors. So I move this vector over here, and it's going to go what? 1, 2, 1, 2, 3. Looks like the resultant vector is this vector here. So this is V, this is U, and this will be U plus V here. And you can draw in the whole parallelogram if you wish. That's what 3 was. That was 2. 3, I want to find V minus U, right? So let's draw V and U. 1, 2, 3, 1. 1, 2, 3, 4, 5. That's my V. And my U is 1, 1, which is kind of there. But I want to subtract it, right? So that means I really want to go minus 1. Yeah, because I'm not drawing this very carefully with a ruler like I probably should, or on a computer, you can't really see. So this is U, and I'm going to move that vector up here, kind of like this. So the final vector is going to be, this is really drawn badly. Try again. Yeah. mean, I don't expect you guys to do this. This nice little graphical program here. Graph, show grid. Okay. And so, graph plot points. So what points am I going to need here? 3, 5. Do this step by step for you.
If you expect us to see something,
Oh,
just
it's
let you
not?
know we
Oh,
we
I'm
know.
sorry. Thank you. My previewer here doesn't seem to work, which is why I'm so far off. Oh. Got it plugged in. Ta-da. Okay. Okay, so here is that point 3, 5, and here's 0, 0. So I'm going to draw that vector. Okay. And then, just put a little arrow on here. So that's my B. And now, I have to plot another point. So -1, -1. So that's this vector down here.
One.
Yeah, that didn't work. -1,
But U is 1, 1, not -1, -1.
Oh. Well, yeah. Let's see. One. Okay. So this is the other, I guess this wasn't the best example because it requires kind of a precise drawing. Okay. So that's my vector 1, 1, but I want to subtract. So really what I want to do is I want to subtract its opposite, which is, that's the -1, -1. Right? That guy, okay? Let me make that a little more distinctly here. Okay, is that kind of visible? So I want to take this vector here, that goes -1, -1, and plop it over here. And if I were to do it graphically with a pencil, I just kind of draw something here. But since I'm using this little magic program, really what I want to do is say 4, 2. That can seem to work. Oh, 2, 4. 2, 4. What am I doing wrong? Plot points. 2, 4, plot. Okay. So here's that vector moved over. So its tail is now at the head of the first vector, right? And now the final vector, the one that I'm going for, is over here. There it can kind of see how the parallel, they can draw the whole parallelogram, it's kind of skinny. All right. You should know how to do this, but doing this well is not a skill that, you know, you will need in your future mathematical life. Okay, those are the only two we can do. We need a little more information to go on. So let's do that. So we've added vectors, we've subtracted them, we found their opposites. Now we want to do something called, we want to get into multiplying vectors. There's different ways to multiply vectors. One way is called scalar multiplication, which, remember, scalar is just a number. So, switch over here. Oh, there we go. So here we have a vector v, and I want to multiply it by 2. So I just stretch its length by that factor, its magnitude. Right? So now, if this is vector v, then from here to here is now 2v. Okay, that's pretty straightforward. If the vector, if the scalar were minus, well, again, I stretch the length of the vector, that amount, but in the opposite direction. That's what multiplying by -1 does. It gets you the opposite. Okay, there's something missing here. So, how would I multiply a vector in component form? That's real easy, just like adding in component form. I want to multiply vector A, you know, in component form AB times K. I just multiply each of the components times that constant. Again here you can see that I want to multiply a vector times -1. That's just, you know, AB becomes -A minus B, right, which is the opposite vector, the inverse vector. Okay, a little more fun algebraic stuff. Distributive laws. There are actually two distributive laws for vectors when you're doing scalar multiplication. So if you want to multiply k times the sum of v plus u, you can distribute the k over. That's just k times vector v plus k times vector u. After a while, this starts to feel really natural. Now, normally when you see stuff like this in a math class, an upper level math class, the first thing we want to do is prove it. And I'm going to show you what a proof looks like. You don't have to reproduce this, but what I'm going to do is use properties of numbers and what I know about vectors to prove this. So, here we go. I want to multiply k times the vector v plus u, and I'm going to write the vectors v and u as vx, vy, and ux, uy. That's their x and y components. So how do I do that? Well, I know that I can add two vectors like this, vx plus vx, vy, ux, vy. I can add them by adding their xy components. So I get this component vector vx plus ux and vy plus uy. That's just one vector. I know from my definition of multiplying k times a vector that I can bring that k in. So I have k times vx plus ux, k times vy plus uy. Now notice that vx and ux are not vectors. They're just component numbers. They're just numbers. So at this point, I can use my distributive property from numbers to say k times vx plus ux is kvx plus kvux. And the y component is kvy plus kvy. Now I'm going to use, my vector addition kind of in reverse. I'm going to separate them out into two vectors, right? I'm going to separate it into the vector kvx, kvy plus kux, kuy. And now again, I'm going to undo the multiplication, kvx, kvy, and kux, kuy, and I end up with k times the vector v plus k times the vector v. So basically, I've gone through all this detailed step to get just from this step down to here, which is what I wanted to prove. Okay, there's another distributive law that's very similar, but instead of adding the vectors, I'm adding the scalars. If I have two scalars, k and l, over the vector v, I can distribute them. That's just k times v plus l times v. Anyone wants to do the proof? I will review it for you after you're done. That's not necessary. Okay. We have just a few more things we need to do here to kind of complete today's basics for vectors. The first is we have a definition. A unit vector is a vector whose magnitude is 1. Or I would write it this way, B unit vector, magnitude is 1. That's pretty straightforward. It's nice to know that if you have a vector and you want to find a unit vector in that direction, there's a really easy way to do it. If you take a vector v and multiply it by 1 over its magnitude, that's what this is, right? 1 over the magnitude of v. This is just a number, right? This is like the k. You get a vector in the same direction, but it's a unit vector now. Okay, so that's unit vectors. By the way, some of this stuff I'm going to say, I'm just going to say it, and you're going to look at it and go, what's that for? And everything I'm doing today is going to show up on Monday. Right? So keep that in mind. We will run into unit vectors. Okay, there are two special unit vectors. These come up a lot in engineering. We give them special names. There's the unit vector I and the unit vector j. And when we get into 3 dimensions, we're going to have the unit vector k. And these have this form. I is just 1, 0, and j is 0, 1. So let's look at these vectors on a graph. I is just this length 1 vector along the x-axis, and j is again a unit vector length 1 but along the y-axis. These are very special vectors in that they can be really handy me show you why. If I have a vector v in component form AB, I can write this as the sum of scalar multiplication of A times vector I plus scalar multiplication of B times vector J. Right, what do I mean by that? If I multiply A by vector I, which is 1, 0, and I add it to B times vector J, which is 0, 1, well, what do I get? Well, here I get A0 plus 0B, which is just my vector AB. Now, this really doesn't do things that differently, right? In this case, the first form, the components you can see are where the position vector, where its head is at. Here, we just have two numbers A and B times these two vectors. They're really just two ways of looking at the same thing. And in some problems, you know, one of these will be more convenient than the other. I mean, they both break up the magnitude into an A direction, an X direction, and a Y direction. But again, this is very common usage, and again, you'll see it in science, engineering, very commonly. Okay, there are two physics problems I want to show you from the book. These are problems that are going to be on homework and are problems that you might be asked to do something like on a quiz or a test. So, the first problem comes in two parts. It's an aviation problem, so remember we're going to use angle in kind of a different way. The first problem says that there's an airplane that is traveling south at 80 miles per hour. 80 miles per hour. Mental exhaustion, I'm sorry, is setting in here. Let me try this again. An airplane is traveling south at 80 miles per hour. And it's going to travel for how long? 2.5 hours, right? 2.5 hours. So the distance it's going to travel, which is also it's a displacement vector, is going to be just 2.5 times 80 miles. So
Is this a car or airplane?
Sorry?
80 miles?
80 miles per hour. So 80 miles per hour times 2.5 hours is just going to be equal to 200 miles. Right. So now we introduce into the problem a little reality. There's a wind that's blowing east at 25 miles per hour. And let's just say the pilot doesn't know about that wind. So these are two velocity vectors, and we want to know where is the plane going to end up now, having traveled 2.5 hours. Well, let's do this as component vectors, right? The first vector is 0, minus 80. Oops. Thank you. That's the, let's say, velocity plane. And we want to add that to the velocity wind, which is, well, I'm not using, what's that? I'm just using the same grid, right? So that's going to be 25 times 0. And so the resultant vector is just 25 comma minus 80. All right, so now we want to find out what is the magnitude or norm of that vector. So that's going to be 25 squared plus minus 80 squared square root. So what do we come up with? Oh, I'm glad this happened. This is a different TI-84 plus. And if yours is like this, you gotta be careful. Say 25 squared on this, and when you say plus, you're adding to the exponent. You have to hit the next. Does anyone have this kind of calc? Yeah, you already know this, right? You gotta be careful. Plus, we don't really need the minus, right? Because we know that's gonna go away when we square it. Okay, so let's just say approximately 84 miles per hour. So that's the speed we're going. Now we'd like to know what direction are we going. So if we use the terminology in the book, this guy is going west, the airplane is going south, the wind is going west. The sum of these is going to kind of look like this. And we're going to say this angle is south of west. Is that what they use? Or do they use south of? I think they're. The question is, do we want to find this angle or this angle? This angle we would say is south of east, and this angle we would say is east of south, and they're complementary. So it's just a matter of using a little trigonometry, of course. The cosine of this angle here is going to be, what, 25 over 80? So theta is inverse cosine of 25 over 80. So it is inverse
Can you move it
cosine.
up a little bit,
Oh,
the page?
sorry. First cosine of 25 divided by 80. So this angle here is 71 degrees. So the direction we're going is 71 degrees south of east.
80 is the one going directly down.
80 is right, going directly down, 25 is going upwards. So again, we're just adding the vector, finding its magnitude, and finding its direction. Now that tells us that, so the next part of the question is, how far off are we from where we wanted to go, right, after 2.5 hours, right? So 2.5 hours, we've traveled 200 miles in this direction, but we've also traveled, because we get blown along with the air currents, we're now 2.5 times 25 miles per hour east of where we want to be. All right, so that's 2.5 times 25. 62.5 miles off course. All right, so that's an example of a vector problem where it tells you what you didn't want it to. Right? The real problem you want is, hey, I'm traveling I'm traveling south, but the wind's blowing me this way. So I'm going this way, right? So really what I want to do is figure out which direction should I go so that I don't get blown off course, right? So, yes. Someone was telling me what I wanted to do. Speak up, please.
One like faces and greens, which will cause you to of course, you want to go.
Yeah, you want to go in this direction so that, again, I can still only go 80 miles per hour, right? But I want that plus the 25 mile an hour vector to get me back to where I'm going, right? So the question is, first, what angle should I be going at?
The same.
It's going to be the same, that's right, 71 degrees, right? Now here's the question, how long is it going to take me,
The same.
right? Well, I want to add these two vectors now. And find out what the magnitude is and divide it by 200 miles, right? You know, again, I'm going to apologize. Just asked me to do this.
But just going.
Yeah. You can do it for homework, all right? Or you can look it up and there'll be a homework problem. We're not done yet. We're not done. I said I'm too exhausted to do this. There's a different problem that we're going to look at. And there are plenty of these problems that you're going to see in your physics class and a few in this class.
Can you submit online if you feel exhausted? You might just make a mistake again for the next one. So you can just give us the answer in the online and you can go. And you have a rest.
I can't even hear what you're saying. I can't, I'm sorry. My brain is just not working right.
Can you say?
Can I say what?
No. Can you post it online? And
Oh, yeah, okay. Well, I mean, I could do that if you wish, or I could just simply post
The answer.
page 665 where what was the problem?
Yeah.
That works perfectly.
It has functions.
Page 665. Does that work?
Yes.
Okay. As messed up as my head is, I can do this next problem for you, and it's an important class of problems in physics. I'm going to call these zero force problems. In physics class, you'll get non-zero force problems where something is accelerating. But the basic idea is, if you have a bunch of forces and something's not moving, those forces have to add up to 0, right? So, for example, I'm pushing on the wall, but the wall is pushing back, right? Exactly the opposite, right? Because I'm not moving. So, the problem from the book kind of looks like this. You have a hot air balloon, which is, because it's that hot air, it's lighter than air, and there's a force upwards of 400 pounds. Pounds is a force. You want to, the balloon isn't moving, so we know that there's some kind of force holding it down at 400 pounds. But we don't have a rope. If we had a rope holding it down, that rope would be being held at 400 pounds. But we don't have a rope. we have two ropes. One of them is at a 45-degree angle. The other is at a 25-degree angle. And it's not moving. So all these, the force for these two ropes is exactly offsetting the 400 pounds upwards. But this is a two-dimensional force, right? It's both up and down and side to side, which means that, one of these ropes is pulling with a certain force this way, and this rope has to be offsetting that exactly. Okay, so we're going to figure out, what we really want to know is what are the force, let's call it force 1 and force 2, what are the forces on these two ropes? As you make this kind of a practical thing, there's some people holding the ropes, right? And how strong do they have to be, or how much do they have to weigh? All right, so the way this looks when you draw the vectors is you've got one vector here, which is 25, this is 45 degrees. You've got one here which is 25, and you've got a force here of 400. So the way you do this is you take each of the forces of the ropes and you break it up into its components. So let's call this rope 1 and this rope 2. And we'll call this the x component of R1. We'll call that x1. And the y component we'll call y1. For this rope, it has an x component, x2, and a y component, y2. Now, what do we know about these components? We know that, or of these vectors, we know the magnitude of x1 has to equal the magnitude of x2. Why do we know that? Because it's not moving, right? If one of these components was greater, it would be moving, right? Sideways. Right. Now, there's something else we know about y1 plus y2, or the magnitude of vector y1 and y2, is the components of it, right? What is it we know? Equals 400. All right, so with those two equations, we're going to come up with two equations and two unknowns, and we're going to go back to algebra 1 to solve this. All right, but first we have to figure out what these guys are in terms of the angle, right? So what is x1 in terms of either this angle 25 or its complement, which is 65? X1 is what, well, what is the value of x1 in terms of the force on, I guess I should give these names, we'll call it force 1 and force 2. Force 1 is what we call it the tension in the rope, and F2 is the tension in this rope. So this is a component of F1 in the x direction, and y is the component in the y direction. So what trig function is going to tell me what relate x1 and F1?
Cosine.
Okay, good, cosine. So how does that work? The cosine of 65 let me write this over here. Cosine of 65 is what? It's the magnitude of x1 over the magnitude of f1. Right? How about x2? Well, here we have 45 degrees. So it's the same thing. Cosine of 45 degrees equals the magnitude of x2 over magnitude of f2. Well, cosine of 65 and cosine of 45 degrees are actually numbers. Cosine of 45 degrees, we actually know the exact value, but let's just leave them, in that form for the moment, right? So over here, I can plug in for x1 and x2 using these equations. And here I multiply by f1, and I can say magnitude of f1 times the cosine of 65 degrees equals f2 times the cosine of 45 degrees. All right, now I have f1 and f2 in an equation. I mean, those are the unknowns, right? The tension of f1 and 2. So now I want to have another equation, right? Right. So I want to know what y1 and y2 are. Well, if x1 is cosine 65, what's y1 have to be? Sine 65 is what? y1 over f1. And likewise, over on the other side, sine of 45 is y2 over f2. So I'm going to do the same trick. I'm going to solve for y1 and y2 and plug that into this equation. Right, that's going to tell me f1 sine of 65 degrees plus f2 sine of 45 degrees equals 400. So it looks kind of ugly right now, but I'm going to rewrite this so it's going to be nice, right?
Excuse me, I have a question.
Yes.
Why is x1 equal to x2?
Okay, so look at the diagram, right? x1 is the component of this rope going this way.
Yes.
x2 is the component going this way.
But isn't x1 smaller than x2 because it's 25 degrees?
We know these angles, right? But we know these two, we don't know what the tension on these ropes are yet. That's what we're going to figure out. But we know x1 and x2 have to be equal because, x1 is pulling this way, x2 is pulling this way, and if they weren't exactly equal, the balloon would move, okay? Remember, these are, I guess I should say, zero force, motionless. Whenever all the forces add up to zero, nothing's moving. I guess the key thing you have to know from physics is if you have a non-zero force, something's going to accelerate. Okay, so we're almost there. Like I say, this is kind of ugly, but I'm gonna make this look much more familiar, right? I'm gonna call f1 x. Forget the x's we've been using. X cosine 65 degrees equals y. That's my f2. Cosine of 45 is 1 over the square root of 2. And then my other equation is x sine of 65 degrees plus y. Well, again, sine of 45 is 1 over the square root of 2 equals 400. Oh, now that looks like something, like I say, from your Algebra 1 class, except the numbers are kind of ugly. That's all right. How would we solve this if these were nice numbers? Well, there's two ways, right? Substitution and elimination. Nobody said use Kramer's rule. Anybody know Kramer's rule? I don't know Kramer's rule. But anyway, it uses matrices, correct? So let's solve for one of these. Let's say x equals y over cosine 65 square root of 2, right? Let's substitute this now in over here. So we have y cosine 65 square root of 2, and on top we have sine 65 plus y 1 over the square root of 2 equals 400. All right, now we're going to take out our y, right? Sine 65 degrees over cosine 65 degrees over the square root of 2 plus 1 over the square root of 2 equals 400. Okay, now I'm going to, you can just plug this in, you can now divide by this and plug it into your computer and get it. But I'm going to do something, simplify it a little bit. First I'm going to multiply through by square root of 2. Put the square root of 2 over here, right? And then I'm going to look at that sine 65 over cosine. This is tangent. This is tangent plus 1. This is really y, 400 over the square root of 2 over the tangent of 65 degrees plus 1. Okay.
Question, sir?
I'm sorry?
Question.
Yes.
You just factored the square root of 2 out of the internal bracket, right?
Actually, I multiplied both sides by the square root of 2. So it was on the bottom over here, and now it's on the top over here.
Okay, because the way I thought about it, I thought you factored the, oh, yeah, okay, that's it.
That
Sorry.
work?
Okay.
Okay.
Sorry.
All right, so we're almost there. Let's, remember y was this guy. That's the F2. Okay. So 400 pounds times the square root of 2 divided by 1 plus tangent of 65 degrees. And I get, let's say 180 pounds. Okay. That's my y. I want to go back to my other equation now. Right? Let me copy that equation over here. My first equation was x cosine 65 degrees equals y over the square root of 2. And now I know my y. My y is 180 over the square root of 2. So x should just be 180 over the square root of 2 over the cosine of 65 degrees. The thing is to not get thrown by the ugly looking numbers, because you're just going to pop them into your calculator. 180 divided by square root of 2 divided by cosine of 65 degrees, 301. Okay, let's go back to our original diagram just to do kind of a sanity check here. So F1, that's 301 pounds that I'm pulling in that direction. F2, that's 180 pounds pulling in this direction. And we could check, but the components x2 and x1, well, let's just see what that component is. That's the cosine of 65 times the cosine of 65. So that actually should be 180 127 in each direction, right? So we're actually, we've got these guys on the ground pulling here and they're pulling there, and they're pulling a lot more than they would if they were just pulling 400 down, right? And they're pulling against each other, right? But that's kind of the way it is with ropes. Now, if you think about it, the closer these are together, right? You move them together, the less they're pulling against each other, and the more, the total amount they have to pull is just going to be half of the 400 as you pull these ropes together. But if you start pulling them out this way, the amount you're pulling down is always 400, but you're pulling more and more and more, and actually, for you to get to where the balloon is on the ground, if you're just pulling outward like that, how much force would that take? Anybody have any feel for that? A lot, right? Yeah. It's actually, it goes to infinity, right? Actually, like if you have a force going up this way, right? And you want just, the y component is always going to be the opposite of the, how much the balloon is pulling up. But if you're going to try, you can't pull like this enough to, straight across to have any downward force at all. So you'd actually have to be pulling infinitely. Now, just a little less, and it's not. So it goes to infinity very fast. But you really can't do it, is what that means. Okay, there's going to be a problem like that on the homework. And a little vector adding stuff. What am I going to say? The assignment, if you want to look at the website, on the website, I don't even have a page here. It's on 670. I know people are already escaping, but I did have one more thing I wanted to say. What we've done today, kind of using the language of vectors, we kind of redid what we've been doing with trigonometry and triangles. On Wednesday, we're going to, you might say, well, why bother with that?